Hi everyone, I hope you are doing good. So today in this tree series we will take a new DSA questions, and that would be predecessor and successor. So here let's understand the question first. Uh, so one BST will be given, and you have one key also, integer key also will be given, and we have to find the in order successor and in order predecessor of the given key. If either predecessor or successor is not found, then set it to null, right? And what is the predecessor and successor? So the definition is given here itself. In order traversal, the number just smaller than the target is the predecessor, right? Target means the key, whatever will be given, right? So just smaller than the key would be the predecessor, and the number just greater than the target is the successor, right? So let's understand this question using the given examples here. So you have to keep in mind this is the in order predecessor and in order successor. The question might be like you have to find the post order successor and predecessor. It could be like pre-order successor and pre-order predecessor. So but here the question is in order, right? So that you have to keep in mind, because interviewer might change the question, correct, but the concept would be same for all. It could be either in order, pre-order, or post order, or level order, right? Correct. So here it is given in order. So here this is the example. So let's understand the question with example here. So it is saying it should be in order. Like this is the question is looking for in order predecessor and in order successor, right? So we have to first get the in order output of this tree, right? So what would be the output of in order? So let me see here. How do we go for in order? So this one, right? So we encountered with 1, so 1. Then we encountered with 3, right? Then 4, correct? And then we will go up, and here this is 8. Then we will go down, and this is 9. And then we will come here, and this is 10. And now we are out of the tree, right? So this would be our in order output of the tree, in order traversal basically, correct? This technique I have already explained in my previous videos as well as. So if you are directly looking this video and if you are having any difficulty while understanding how we are getting this in order traversal output, right? 1, 3, 4, 8, 9, 10, correct? Then you can go and check out my previous videos as well, correct? So now here the key is 8, right? Key is 8, and we are looking for the in order predecessor and successor. Predecessor means less than, smaller value, right? Right? And successor means greater value, correct? So key is 8. This is our key, and just less than this one, just before the smaller value of 8 is 4. So this would be our predecessor, right? And just after the 8 it would be 9, right? So this would be your successor value, correct? I hope you are getting it. First you have to take the in order traversal of this one, in order output of this one, and then you have to find the key, or you have to find just a smaller value than the key, that would be your predecessor, in order predecessor, and just the greater value, right, than the key, that would be your successor value. I hope you are getting it. Let's take another example, right? So what would be the in order output of this one, this tree? Let's draw these lines here, and then we will go from up, like we will traverse the tree. So we will start from here because we are talking about in order. So we encountered 1, correct? Then we will go up, and here we encountered 2, right? We will go down 3, right? Then we will go down, then 4, right? We will not cross any basically edge or connection, right? And traverse each and every node. So we will go up, and here we encountered 5, right? Then we will go down, and here this is 6, and then we will go up straight, and this is 10, and then one more node, this is 11, and then we are out of the tree. So this would be our in order output of the given tree, this one, right? 1, 2, 3, 4, 5, 6, 10 and 11, right? These are the nodes. 1, 2, 3, 4, 5, 6, 7, 8. 3, 3 and 8, correct? So this is our basically output of the in order. Now we have to find the in order predecessor and successor, right? And our key is 11, right? Our key is this one. This is our key. Now smaller value, just smaller than this key is 10. So this would be our basically predecessor, correct? And what about successor? So here nothing is there, right? Here nothing is there. So what would be successor of this one? So successor would be -1, right? That is what it is mentioned, right? You have to set the null value. See, right? If see here. So if successor is not found, then set it to null, right? And then the main function, that the driver function, will make that null to -1. That is what it is coming here, right? So it would be null here. Correct. So I hope you understood. It is very simple. It is not a rocket science, right? You have to just take out the in order traversal, in order output of the tree, and just smaller value, that would be the predecessor, and the just greater value, that would be the successor of that key, given key. Correct. Now think about the solutions. What could be the algorithms which can be applied here to find this predecessor and successor? What is coming in my mind for solving this problem is, first is, as we have understood, we are taking the in order traversal, right? So we can go through the in order traversal as well as, right? We can take the complete in order traversal, and so for this case example, right? So here the in order traversal would be, we just saw, right? 1, 3, 4, 8, 9 and 10, right? So we can take this in an array, correct? And then we can look for the key, that is 8, right? That is 8. So and then we can find the smaller value, and then we can find the greater value. So this is the one way where we can go first in order traversal, right? In order traversal, and then in second iteration, what we can do, we can look for the predecessor and successor, right? So this is the one way. But here the time complexity would be like, here what is the drawback of this algorithm, this solution, is that we have to traverse each and every node of the given tree, correct? That is what the drawback of this one. It means the time complexity would, in each and every case, it would be order of n, right? We have to go and check all each and every node of the tree, right? Can we optimize this solution? Yes, we can, because we have to find, because we have the key, right? So first we have to look for that node, and once we found the node, then we can just find, because we know the property of binary search tree. It is a binary search tree, it is not a binary tree, right? And if it is a binary search tree, it means the left node would be always less than the root, and the right node would always be greater than the root, right? Whatever the node is, right? Correct. So each and this property will be applied for each and every node, correct? So using this property, we can optimize it into the, from order of n to order of h. H would be the height of the tree, binary search tree, right? And this h would be like, if this is a balanced tree, in that case it would be log n, right? And if it is skewed tree, right, this way, in that case it would be order of n, correct? So it depends on the tree, but in the best case we can achieve it is to order of log n time complexity. So that is what we have to optimize, right? Else it is very simple question, right? If we go with the order of n using the in order traversal, right? And same applied for the pre-order, successor, predecessor, in order, and post order or level order, in order, predecessor, right? So that is what you have to keep in mind. So first you have to start with the order of n time complexity. You can tell the interviewer, yeah, this is the one approach which came into my mind. Like we can take the in order traversal output, and then we can look for the smaller and the just greater value from that that output, right? And that would be your predecessor and successor, and the time complexity of that would be order of n, correct? Now what would be the optimized solution, right? I hope you know the in order and this in order traversal. So that would be that you can do by your own, correct? So what would be the optimized one? So what I will do, first I will find the predecessor, right, and then I will find the successor, right, in two iterations, correct? So for predecessor, let me add one code here. What I will do here, I will add while node, right, correct? And here what I will do, and node would be this one, right? Node. So let me take it n only, so that would be easy, right? N, right? And n is root initially, correct? So now we are here at 8, right? And our key is 8 here. So here I will add if, because we are first finding the predecessor, right? Take it p only. So predecessor. So now predecessor always with the less value, less than the key, right? So smaller, which side we will get smaller, right? If the key is this one, right? So smaller value will always be in the left side, correct? So if here node arrow data if node arrow data is smaller, right, is smaller than the key, right, it means we found one value which is less than the key, but now we have to maximize that one. So first this one, right, if so here, if this one, that we can update the or predecessor, right, p is equals to node arrow data, and now we can go to the right side, right, node is equals to node arrow right, else node is equals to node arrow left, right? Why I am going right side? Because we found one value which is less than the key, whatever key is there, that is 8, right? But now we have to maximize that one. That's why I am going right side, because right side we will find the greater value, correct? I hope you are getting it. So let's try run this algorithm for predecessor. Here key is 8, right? Node is initially at 8, and this key is also at 8, correct? Now this condition node is not null, right? So we will go inside the while loop, and then here node arrow data is less than key. No, it is not less than key. So we will go to the node arrow left, right? Now we are coming here node arrow left, right? 1. So see here now, 1 is node arrow data, that is 1. 1 is less than key, yes, because key is 8, right? And node arrow data is 1, right? So we will update the predecessor. Now predecessor is so take it p, predecessor is now 1, right, because 1 is less than the 8, correct? Now here we have to, we found the predecessor, now we have to maximize it 1, right? So so we will maximize it, so we will go to the node arrow right. So here from 1 we will go to here 4, right? So now we are here at 4, correct? And then again we will go up and check, yeah, node is not null, node arrow data is less than key, yes, correct. 4 is less than 8, right? 4 is less than 8. So we will update the predecessor is 4 now, and we will go to node arrow right, and again we will go to here, again we will try to maximize it 1, because this is still less than the key, correct? And here we will get the null, right? Once we are getting null, then we come here at the while and we will check the condition, yeah, node is null, so we will come out from here, and this would be our predecessor 4. I hope you are getting it, right? First we get the less value, right, smaller value, and then we will try to maximize it using the binary search tree properties, correct? And here now see here we are getting 4, and this is our 4 is our answer for the predecessor, right? We found the predecessor now, right? Let's understand this with the, another example as well. So let me clear this one and take one more example with this same algorithm here, this one, right? 11. Now here we are here, right? So n is at 10, right? N is the node, right? And our key is 11, and our predecessor is for example -1 initially, right? So now node is not null, so we will come here and node arrow data. So node arrow data is 10, correct? And key is 11, right? So it is already less than, so we can say we can update the predecessor by 10, right? with 10 value, and then we will go to right. We will try to maximize it one. So we will come here, right, and it becomes 11. So we are here at 11th, this node, correct. So now from here, this 11 is less than key. No, it is not. So we will go to the left side, right, left of this one here, but it is nothing is there, right, from left side nothing is there, so it will be null. So now this 10 would be our predecessor, right, 10 would be our predecessor, because we did not find anything uh, uh, which is less than the 11 and greater than the 10, correct. I hope you are getting it, right. So now this 10 would be your predecessor. So this is for predecessor. Now think about the successor, right. So let's so what I will do, as for predecessor we need the smaller value, that is why first we are checking for the smaller value. Now for successor, what is successor? The greater than the key, right, just greater than the key in the in order traversal. So what I will do for successor, I will modify this value here, as here we are looking for a smaller value. So for successor, what I will do, for successor we will look for the greater value, right. And once we get the greater value, it means now we will minimize that value, right. So that is why what we, instead of right side, we will go the left side, right. And once if it is the smaller value, then we will go the instead of left side, we will go to the right side. These are the changes we have to make in our predecessor algorithm, right. Then it becomes the successor algorithms, right. Then it would become the successor, right, correct. So let's do the dry run here. Don't worry, I will show you the C++ code also, and then we will run the code, right. So here the node, right, here the node is 8, right, we are here, right, and our key is 8, and our successor s is -1 initially, right. Now 8 is greater than key. No, it is not, right, because 8 and 8 are equal, correct. No error data. So what we will do, we will go to the this one. So we will go to the right side here at 9, right. So it becomes 9 now, correct. And now we will check the condition again. So node arrow data, that is 9, is greater than the key is 8. Yes, it is yes. So we found the greater value, correct. So now we will update the predecessor, it would be successor, right. So now we will update the successor value here s, right. So s would be 9, correct. And now we found the greater value. So now what we will do, we will minimize this value. So for minimizing what we will do, we will go to the left side, right. So here node arrow left we will go. So from here we will go, try to go to left, but nothing is there, right. So nothing is there, it means null, correct. So now node, it becomes null, right. And then we will come out from here, and this 9 would be our successor. I hope you are getting it, right. So from 9 we got the 9 is greater value. So now we will try to minimize it one. So that is why we will go to the left side. Left side is nothing, right. We do not have this 9, does not have the left value. So the node becomes null, and then we will go to up, and here we will check the while condition. Node is null, right, here this one. So we will come out from the loop, this while loop, right, and we will say 9 is our successor, and that it is, right. See here output is 9 also for successor, right, correct. I hope you are getting this. Let's try this algorithm for the another example. So here we are here, right, n is at 2, correct, and our successor is -1, right. Now 2 and our key is 3, right. So node arrow data, that is 2, and key is 3. So it is greater value. No, it is not greater value, right. We are looking for the successor, so it is not greater. So we will try to maximize this value, right. We will look for the greater value. So we go to the right side, right, 3. Now it becomes 3. So now 3 is greater than 3 key. No, it is not. We will come here, node is not null, and check it, right. Node arrow data is 3. So node arrow data is 3, key is 3. So now it is not greater than the 3 value, correct. So we will again try to go to the right side, right. We are looking for the greater value, but nothing is there, null value, right. So what we will do, we will come out from the loop, right, and that -1 itself, it would be our successor, right. Because if we do not find any successor, in that case what we are we are printing that is -1, right? And see here, this is the -1 for this value, correct? I hope you are getting it. Instead of -1, we have to return the null value basically in the question. But here that main driver function will convert that null. If it see the null value, then it will print the -1. That's why I am saying -1. Correct? I hope you are getting it. So now let's check out the C++ code. So here I have added the same code whatever we have discussed for predecessor, right? Here this is node arrow data, and that should be less than the key. And here for successor, node arrow data should be greater than the key. If it is greater, then just go for left and update the successor, and if it is less than, just update the predecessor, right? And go to the right side for looking for the greater value, right? Maximize it one, correct? And if it is not the less than value, right, then just go left side to find the minimum value, right, the smaller value for the predecessor. And if the node arrow data is not greater than the key, it means it is less than the key, so it cannot be the successor, right? The smaller value cannot be the successor, and the greater value cannot be the predecessor, right? It is clear, correct? So if it is less than, right, the key, and we are looking for the successor, it means we have to find the greater value. That is why what we will do, we will go to the right side. And we know in the binary search tree, right value is always greater than the node value. That is why we are looking for the greater value, and that is why we are going the right side here, right? So as we have already discussed the code, right, correct? So I hope you got and then after this we are looking for the vector. So both the values, predecessor and successor, I am putting into the vector and I am returning it, right? So that is the algorithm solution. And what would be the time complexity of this one, right? So we have discussed already, for if we go for the simple in order, right? If we go for the simple in order traversal, right? So their time complexity would be order of n in each and every case, because in each and every case we have to traverse each and every node, right? But here in this approach, time complexity would be order of h, right? Why order of h, right? As you know, we have discussed. So here for this key is 8, right? This key is 8, correct? So here for predecessor we traversed here and then here, correct? For the predecessor. For successor we traverse till here, right? So it means we are not traversing each and every node of the tree, we are just going till the maximum, till the height of the tree, right? So time complexity would be order of h. Now it depends on the tree. If it is the balanced binary search tree, right, in that case this h would be log n, right, log n. And if it is skewed, for example this 8, then 9, then 10, right, in this way is skewed either right side or left side, in that case it would be order of n. That is the worst case. So in best case we can achieve order of log n, right? And in the worst case we can achieve order of n. So this is the optimization we did, right? Now if you still have any scope of optimizations, if you know any more efficient algorithms, then please comment below the video, and also let us know about your solution. That's all from my side for this today. See you next time. Till then, keep learning and keep exploring.